Hello everyone, my name is M. Prajwal. I am from CSM B section. Today, my video presentation topic is Fermi-Dirac distribution. Introduction. It describes distribution of Fermions over energy states, and Fermions follows Pauli's exclusive principle. There are three principles are there: Aufbau principle, Pauli's exclusive principle, and Hund's rule. And this Fermi-Dirac distribution follows Pauli's exclusive principle. And no two fermions can occupy same state. For examples, electrons, protons, and neutrons. And it is used in metals and semiconductors. Now let us know about Fermi-Dirac function and a mathematical expression for a distribution and given by f of e is equals to 1 divided by 1 plus e power e minus ef divided by kt, where e is energy level and ef is Fermi energy and k is Boltzmann's constant and t is temperature. Now Fermi energy ef at 0 Coe, it is the highest occupied energy is produced. Importance reference level and at absolute zero, all states below EF is filled. All states above Fermi energy is empty and it determines electrical properties. Let us know about behavior at absolute zero. At temperature T is equals to 0 K, if E less than EF, F of E is equals to 1, and for F of E greater than EF, F of E is equals to 0. Short steps like distribution, no thermal excitation. Now, behavior at higher temperatures. In Fermi-Dirac distribution, let us know about temperature. As temperature increases and distribution smoothness also increases, and smooth electrons moves to higher energy levels, and probability near EF becomes 0.5, and curve becomes gradually instead of sharp, and thermal energy affects the electron motion, and it this at high temperature it will affect the electron motion. Now we can observe the Fermi-Dirac distribution, and the formula is already we know about the formula 1 by e power e minus ef divided by kt plus 1. Now graph explanation. On x-axis we take energy E, on y-axis we take probability of Fe. At low temperature steep curves are formed, at high temperature smooth curves are formed. EF is the midpoint where Fe is 0.5. At steep curves and smooth curves are connected at 0.5. And now comparison with other distributions. Different from Maxwell-Boltzmann's distribution and MB applies to classical particles, Fermi-Dirac distribution applies to the quantum particles. Now already we know about Fermi-Dirac distributions considers Pauli's exclusive principle, and it is more accurate of for electrons in solids. Now we know about applications. Fermi-Dirac distribution used in semiconductor physics. We know about semiconductors. For example, silicon and germanium is the best semiconductors, and it explains conductivity of metals and importance in electronic devices and helps in designing the transistors and used in quantum mechanics in studies. Now, conclusion. Fermi-Dirac distribution explains Fermionian behavior and also based on quantum statics, and it depends upon temperature and energy and crucial for modern electronics and a foundation of solid state physics. It already we know about quantum mechanics in solids. Thank you.